Welcome everyone on behalf of Crossroads Cultural Center. I think you all know that we have a real treat in store for us tonight. So let's get started. Last year, physicists around the world celebrated the 100th anniversary of the theory of general relativity. Without a doubt, the field equations that Albert Einstein presented to the Prussian Academy of Science in November 1915 would have gone down in history as a towering intellectual achievement, even if they had been only partially successful in accounting for our observations of the universe. But what is truly amazing is that, in fact, such a simple and elegant model has since been proved to be consistent with all available astronomical and cosmological data. One cannot think of general relativity without being reminded of Eugene Wigner's famous comment, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve." Fittingly, the 100th anniversary of general relativity was also marked by a new occurrence of this wonderful gift. Last February, the LIGO Collaboration announced the first direct detection of gravitational waves, which until then had been by far the most elusive among the phenomena that Einstein had predicted. This long-sought confirmation of Einstein's most fundamental theory cannot but renew our wonder at the mysterious rationality of the universe, and at the same time at the mysterious power of the human mind to participate in this rationality and capture it in beautiful mathematical formulas. We are fortunate to have with us tonight two distinguished scientists who have closely followed or even participated directly in the search for gravitational waves. Dr. Luca MATONE is a native of Rome, Italy, and received his master's degree in physics from the University of Roma Tor Vergata, and his PhD also in physics from the Université Paris Sud. His research focuses on the large-scale experiment and observatory LIGO in Virgo, whose primary goal is the observation of gravitational waves. On September 14, 2015, the LIGO and Virgo collaboration made the first detection. The observation consisted of a gravitational wave signal produced by a cataclysmic event consisting of the merger of a pair of black holes more than 1 billion light years away. Luca currently holds a research position at Columbia University and focuses on public outreach. He is taught at Fordham University, teaches at Regis High School in New York City, and mentors students in their scientific research. Our other speaker, Dr. Massimo ROBBERTO, is an Aura observatory scientist in the Space Telescope Science Institute in Baltimore and a research scientist at Johns Hopkins University. His main expertise is in the concept, development, and operations of novel infrared instrumentation, both for ground and space astronomy. Massimo's main research field is star formation, the Orion Nebula in particular. Massimo holds a degree in physics and a PhD in astronomy from the University of Torino. And now I bring you Dr. MATONE.
Thank you. It's a great pleasure to be here. I usually, when I speak, I don't speak very loudly, so if you'd be so kind to tell me if you can't hear me. So it's a great pleasure to be here and to talk to you about this particular event that occurred last year. It's a significant episode simply because it wasn't simply the detection of gravitational waves. It actually is for us a different means for observing the universe. And that's why I'm going to entitle these slides, Listening to the Universe. And the way I like to do it is essentially by showing you this image. This image is the view of the night sky, essentially, taken from a very remote area in Colorado, in the United States. And then I have to tell you that for us New Yorkers, it's not a familiar image because for whoever, if we live in cities and things like that, we're not so lucky to look at the night sky like this. We can only see a handful of stars. But anyway, so if you go and you place yourself and you look at the night sky coming from a remote place, like for example this place here in Colorado, you are essentially overwhelmed by the number of stars that are out there. And if you get acclimated to the night sky, to the night vision, to the darkness, you can actually discern the fact that there's a band of lights. And the band of lights, of course, we know it's the Milky Way. The Milky Way today, we know that essentially it's our galaxy. We know that we live within the disk of our galaxy. And when we look up, the galaxies are flat. And when we look up, we look at the profile of this galaxy. So that's what we see, the profile of our galaxy. And again, we get the same image, that we get overwhelmed by the number of stars that are out there. So if you look at this, you see a lot of stars, and then you also see regions that are dark. Those regions that are dark, we know today, they don't correspond to regions where there's an absence of stars. Instead, they correspond to regions of the sky where your view is blocked. Your view is blocked by the presence of clouds, dust clouds, and so it doesn't really represent the absence of stars. And so one thing you could do, for example, you take your telescope and you aim it at the center of the galaxy, okay? And instead of looking at the visible light, what you do is you change and you look at other light, which turns out to be emitted in the infrared. Infrared light has the ability to be able to penetrate dust clouds so much better. And therefore, in the end, you can get a better sense of what is out there, if you will. You still, this is not an image of the universe. Of course, this is just an image of the center of our galaxy in the infrared. And you do still see the presence of these dust clouds. But now you have a better ability to see what's behind them. I can't say that every pixel in this image corresponds to a star. But I can tell you already that I refuse to start counting them. Because there are just so many. And again, I get the same theme. The theme is that in the end, I get overwhelmed by how many stars there are out there. And I have to remind you that our sun is a star. And these are just many, if you will, suns, if you will. And then it's more probable than not that each of these stars at the end has its own planetary system. So if you can build on this and you truly get a sense of you're just simply overwhelmed by the grandeur of, essentially, this is not the universe, this is, an idea of the universe, if you will. You get a picture of the idea of the universe. So I'm supposed to be speaking to you about gravitational waves. Instead, I'm talking about suns and the galactic plane and things like that. So why am I doing this? Well, it turns out that if you are exposed to all of these images, this one, the one before, and so on and so forth, you always get the same theme. And the theme is that if you look at the universe, or if you look at the galaxy and so on and so forth, it seems that they seem to convey a message at the end that the universe is very calm. There's not much going on. If there's something moving, it's moving really slowly, very peaceful, in harmony, that kind of thing. But we know that the universe is not really like this. Actually, there are some truly bizarre things happening in the universe continuously. Okay, and these images don't actually portray them. So last year, another piece of evidence in the end, the universe is actually more violent than we thought. Last year, the galaxy far, far away from here. Okay, we don't actually know how. We don't actually have an idea of where this galaxy was. We have a general idea where the galaxy was, but we know it was truly very far away. that signal turns out the detection of gravitational waves. That signal, okay, gave us also information where this cataclysmic event occurred. And we know that that cataclysmic occurred 1.3 billion light years away. 1.3 billion light years away is a big number. And I have to remind you that 1 light year is the distance that light travels in 1 year. So that particular event, we have evidence that occurred 1.3 billion light years away. But there is more than that. Because if you think about it, if light takes time to travel, that means that this event also, we received it last year, September 14, 2015, last year. We received that signal, but that must have been emitted 1.3 billion years ago. So you're really looking back in time. So you can think about all these things. That cataclysmic event was not actually visible with any telescope. We registered with gravitational waves. I'll show you how we were able to do this. So we essentially had information about this cataclysmic event, and then we provide this information to a computer to model for us what the event was like. Okay, if you were standing not far away from it. Okay? So if this is a simulation that I'm about to play, we are asking our computer to do the following. The cataclysmic event consisted of 2 black holes orbiting around each other to coalesce to form a 3rd black hole. Okay. So the computer instructions were as follows. The information was given to the computer to reconstruct the inspiraling of these 2 black holes and their final merger at the end of the 3rd black hole. Would you be so kind to come to good play? So black holes, they're represented by the dark disks. Of course, no light can escape the black holes. The gravitational pull is so strong that these 2 black holes are able to distort the image of the stars behind them. So that's why the image of the night sky, if you will, from behind is distorted. The 2 are inspiring each other, inspired towards each other, and they finally form a final black hole. Now, if you reconstruct that event, we believe that that event consisted of 2 black holes